Alrighty, let's go ahead and get started. So today we're going to start on linear algebra. This is a very, very big topic, obviously in mathematics, that can be done over a number of semesters, getting deeper and deeper into the subject. We're going to go through kind of the basics today, beginning introductory stuff, and get a little deep into it, at least so far as it is useful in physics. Obviously in mathematics there's a lot of theory involved, but we are doing mathematical physics, so we want to see what's most useful at our level and why we would want to learn this particular piece of mathematics to solve physics problems. So to start off with, linear algebra is of course a form of algebra. And the word linear means that the types of equations that this branch of mathematics will allow us to solve are linear equations. So not quadratic, not cubic, none of those fancy types of equations, but basic linear equations, things like, for instance, x plus 2y equals 5, and minus 2x plus y is equal to 0. And maybe we want to know what's the value of x and y. Okay. Now, of course, basic algebra allows us to do this. We know how to do it. There's several different methods. Of course, there's substitution. You choose one of the equations, solve for one of the unknowns in terms of the other. Take that answer, plug it into the other equation, and now you have a single equation that just has one single unknown in it. You could solve that, get an answer for that unknown. And then, once you have that answer, plug it back into the original equation you started with, and you could solve that equation for the last unknown. And now you have your two answers. And of course, this could be done for even more equations and more unknowns, 3 equations, 3 unknowns, 15 equations, 15 unknowns, and so on. It's just a matter of being tedious, taking time, but as long as you're organized and you keep track of everything and you're careful, this is a basic method that will crank out the answers. Now, of course, a lot of times when you're dealing with real-world applications, really big sets of data, maybe you're doing research into CT scans in medicine. Well, a CT scan is basically an X-ray machine that takes a whole lot of pictures all around the body and then takes the data, solves, dozens of thousands of equations with dozens of thousands of unknowns, and then from those answers it builds up a three-dimensional image of the inside of your body. Now, you obviously are not going to want to do that by hand, so you use computers to solve those types of things. But how does the computer do it? And generally speaking, people program the computers to solve these using linear algebra, which is the use of vectors and matrices and things like this, rather than basic standard algebra. Only because it's faster, it allows the computer to compute much more quickly, and time is a very, very expensive thing when you're dealing with computational physics. So that's one of the reasons we're going to talk about this, but there are others as well. Of course, quantum mechanics, when you get into that, there's a whole version of quantum mechanics that deals with using matrices to solve it. That's Heisenberg's method rather than Schrodinger's method with his differential equations. And plenty of applications. For us, though, let's look into the basics. And once we understand how this stuff works, then as we get into other subjects, we may find this particular branch of math very useful in solving equations. Now, the first thing we want to do is relate this to something we already know very well, and that's vectors. So, in basic general physics, we come up to vectors almost immediately, and the way we usually see vectors is something like this. You've got a velocity, and the velocity, let's say it's a function of time, And so maybe you have an object, that object's moving through space in some way, and we will write this velocity as something like it's moving 2 meters per second in the x direction, 3 meters per second in the y direction, and maybe it's moving downwards with 5 meters per second in the z direction. So this is a three-dimensional vector. It's got x, y, and z components. Remember, if you're not comfortable yet with this stuff, I hat is the unit vector in the x direction. J hat is likewise a unit vector but in the y direction. And K hat is a unit vector in the z direction. Okay. Now, of course, when you first learn vectors, you're looking at things, and I better put my little arrowhead up there. I'm going to forget to put the arrow on top of the vectors all the time, but that's fine. Usually when you first learn about vectors, you see something like this. Vector v is some magnitude of v in some direction, theta, right? And we know that vector basically in the x and y directions here, so this will be two-dimensional. It's an arrow that points out with a certain length, the length being called the magnitude of the vector, and it points at a certain angle theta, right? And then the x component, the I hat part, is this x piece, the length that's only in the x direction. And then the y component of v is how big the y piece, how far up in the y direction it goes. And of course, if we're doing three-dimensionals, the same in the z direction. Now all we've done is, instead of having this notation, we like this notation much better because it already shows you what the x, y, and z components are. If you don't have that, then we have to go and do our little component calculations to get the x component is magnitude of v, cosine theta, that kind of stuff. And of course in three-dimensional, then it's a little bit more complicated, because you have 3 dimensions, so you need 2 angles. But we know how to do it. It's calculations, fine. And we know with vectors, the math is a little bit different. If you want to add 2 vectors, v and u, let's say, then the only way to be able to add them is to only add their components. Because if you remember, the rule we talk about is 2 vectors cannot be added if they point in different directions, at least not directly added. So if these 2 vectors, like this, one goes this way and one goes like that, these 2 vectors can't just be added, because how do you add them? Do you add the magnitudes and add the directions? Do you multiply? How do you do it? You just can't. However, if you have 2 vectors, let's say v like this, and then another vector in the exact same direction, well, that we know how to add. We add the magnitudes, and the direction is the direction. Very easy. So if you have 2 vectors that are in different directions, how do we add them? Well, we remember from basic physics, you add the components. So you would say it's the x component of v plus the x component of u. And that's how much our new vector points in the x direction. And then we have the y component of v plus the y component of u. That's in the j direction, and so on for the k direction. So that's how the math works. That's how the algebra of vectors works. If you're trying to add or subtract 2 vectors, you can't just add or subtract them. If they point in different directions, you have to do component-wise stuff. And that's why this notation right here is very nice, because they're the components. You just add them. X's with the X's, Y's with the Y's, and so forth. If you have this notation, well, first you got to get the components. That's a calculation you have to do for each vector, and then you could do the rest. Now, what we're going to do with linear algebra is exactly the same kind of a thing, only we're going to have kind of a new notation. That's really all it's going to amount to, for now at least, is instead of writing it in these ways, we're going to have some new notation that basically simplifies things, makes it look a lot neater on the paper, but it's the same basic premise. We're going to have vectors, and we're going to do work with these vectors. So what does it look like now? Well, now, if we have the vector v, and let's say it's a in the x direction, plus b in the y direction, plus c in the k direction, or the z direction. Another way I could write it is what's called a column vector. Okay, so we're going to have a column of numbers. The top number reflects the x component of this vector, so that's going to be a. The middle number is going to be the y component, which is b, and of course the last number is the z component, which is c. There we go. So these two things, this guy and this guy, are exactly the same thing, just written symbolically different. Okay? It's understood when you see a column vector. If we're talking about, vectors in physics, that kind of a thing, and not some abstract version of a vector, we're going to be thinking about this physically for now. If we see a column vector, then we just assume each element is a different component. The top element is x, then y, then z. And if there's more, let's say we're doing special relativity, so there's 4 components, then you have, depending on whose standard you do, time, then x, then y, then z, and so forth. You could have a length 10 vector, and fine, whatever that means, maybe you're doing string theory or whatever, you have 10 dimensions, there's your 10 dimensions. Each component is its own little element of the vector. And so, if we have two vectors, v and u, let's say u is d in the I direction, e in the j direction, and f in the k direction, well, we can rewrite that as d, e, f, like this. And so, if we want to add two vectors, v plus u, that's the same as saying I want to add a, b, c, plus d, e, f. And that's going to give us a vector, so it's going to be a column of 3 numbers. The top number is adding the x's with the x's, so a plus d. The middle number is adding y with y, so b plus e. And then finally the z's, z plus f. Okay? And of course, if these are regular numbers, we just add the numbers and it'd be single number per element. Here, because these are generalized things, it just kind of looks a little ugly. But that's the answer. Just like before, no different. It's just instead of writing I hat, j hat, k hat, and all that stuff, we just write these little column vectors, and we understand that each element is its own component. And likewise, if we're going to subtract two vectors, then instead of v plus u, it's v minus u, so it'd be a minus d, b minus e, and c minus f, and so forth. Okay? Well, what else can we do? There's more things we could do. How about multiplying? What if we have, let's say, a vector v, which is a, b, c, and I want to multiply it by some number. Let's say I want to multiply it by the number alpha. So now I have alpha times the vector v. Now alpha, this is going to be a scalar, a number. So like 5 or negative 7.3 or something like that, not a vector. I'm multiplying a number times a vector here. How do we do it? Well, it's written alpha times a, b, c, like this. And to actually get the answer, it's the same as writing the vector alpha times a, alpha times b, and alpha times c. Each element gets multiplied by this scalar. Okay, so you don't just multiply one of the elements, you multiply every single element by this number. Okay, now obviously this is not as pretty, so what we usually do when we do linear algebra is when we have something like this where each element is a multiple of something. So let's say we have something like let's say 8, 20, and 16. Notice every element here is a multiple of 4. Then we could factor out the 4. And so 8 divided by 4 is 2, 20 divided by 4 is 5, and 16 divided by 4 is 4. So this and this are the same vector, right? Well, this with the 4 multiplying it. It's just that instead of having such big numbers on the left, I could factor out what's common, and then that simplifies the numbers, right? It's the same thing as if you have something like 5 over 20. We just rewrite it as 1 over 4, right? These are the same things. It's just one's simplified and one is not. So usually you don't see this, you usually see that. That's just prettier on the page. Okay? But that's scalar multiplication. You have a vector, you want to multiply that vector by a scalar, so maybe it's something like this. The vector is how far you have to walk to get to the store. So you have to walk, A miles in the x direction to the east and B miles to the north. And that gets you to the store. And then someone says, okay, well, this other store is twice as far away in the same direction. So how far would you walk? Well, the magnitude, the vector itself, is multiplied by a factor of 2. You're walking twice as far. What does that mean? That means each of your components gets multiplied by that number, by that scalar of 2 or whatever. Okay? So you have a vector, you say triple the vector, that means multiply the vector by 3. That means each component is multiplied by 3. Okay? Well, what else can we do? Another thing we could do is what's called the dot product. Okay. Dot product is similar. It's a form of multiplication, but this time, instead of multiplying a vector by a number, we're multiplying a vector by a vector. So let's say we have the vector u. Better keep the same notation. V, which is A, B, C. And the vector u, which is D, E, F. Okay. Two vectors, V and U, and I want to multiply by the dot product, V times U. What does that mean? How do we do something like this? Well, just like when we're adding vectors, the way you do it, the rules, the operations you have to do that are different for vectors than they are for scalars. You want to add two numbers, 2 plus 3, that's easy, 5, very easy. You want to add two vectors together, not so easy. Do the components, add the components together first. Same here with multiplication. If we want to multiply a vector by a number, very easy. Just take each component, multiply it by that number. But now we want to multiply a vector by a vector. That's not so easy. There's actually two different ways we're going to learn to do this. The first is what's called the dot product. Also sometimes it's called the inner product. You see this a lot in quantum mechanics. So the dot product. And the reason it's called the dot product, of course, is because the little operator symbol is a dot. Well, to do it, let's write it. A, B, C, dotted with D, E, F. Now, we see how to do this in physics when, let's say, we're talking about work. Work, if you remember, is equal to force times distance. F dot x, the dot product between force and distance. So if you have some block with a mass m, you apply a force F, and that block moves a certain distance x, then the amount of work you're doing is the dot product between the force you apply and the distance it moves. And it's the dot product because maybe the force is not straight ahead with the distance, but maybe you're pointing at an angle. Maybe your force is kind of downwards or upwards. Maybe you're pulling a wagon, and so it's just natural that there's a slight upwards force along with the pulling force. Well, it turns out in physics, the work only depends on how much of the force is in the same direction as the distance traveled. So any amount of force that's perpendicular to that doesn't count in the work. Well, it turns out that to properly calculate it, if we're going to think in vector terms, is to multiply these two vectors, the force you're applying to move the object and the distance the object moves while you're applying that force. That form of multiplication is the dot product. And we saw how to do it with general physics. Now we're going to look at it in terms of linear algebra. And it turns out that the answer you get in a dot product between two vectors will not be a vector. Unlike this form of multiplication, scalar multiplication, where you take a vector, multiply it by a number, you get a vector as an answer, right? You get this little column vector right here. Well, with a dot product, that's not true. The answer you get is going to be a scalar. Just a number. You start with two vectors, you do some form of multiplication, and you just get a number as your answer. Okay, so how do we do it? Turns out, with this notation, it's very, very easy. If you want to do the dot product between two vectors, you multiply the x component of the two vectors together, so a times d. Then you add that to the multiplication or the product of the two y components, b times e. Then you add that to the product of the two z components, z times f. You add these numbers together, you get some final number. That is your answer. That's how you do a dot product. Again, back in physics days, general physics, the dot product or the work between force and distance, usually for the simple questions, the distance traveled is, let's say, the x direction. So you just multiply the x component of the force times the distance, and that's your answer. But let's say this is, maybe we're out in space and we're moving a rocket ship or the space station or something. And so we're applying thrusters in different directions and the object's moving in certain directions. So it's a completely three-dimensional problem. So what you have to do is you say the amount of work done in the x direction plus the amount of work done in the y direction plus the amount of work done in the z direction is the total amount of work done. So you take the x component of f times the x component of the distance traveled, plus the y component of your force times the y component of the distance traveled, plus the z component of your force times the z component of the distance traveled, right? So x times x plus y times y plus z times z. That's how you do the dot product. And then, of course, if we do it the other direction, u dot v, and we should worry about this because although we're comfortable with normal numbers, basic rules of math from, grammar school days, where we have things like commutative property, we're under the assumption that if you take a times b, that's the same as b times a. We don't know that that's true with vectors yet. We have to show that it's true or prove whether it's true or not. So well, let's see. U is d, e, f, dotted with v, which is a, b, c. And so we get d times a plus e times b plus f times c. And of course, because the elements in our vectors are just numbers, a times d is indeed the same as d times a. And b times e is the same as e times b. C times f is the same as f times c. So yes, these two answers will be the same. So it turns out for the dot product between two vectors whose elements are just regular numbers, you could do, it is commutative. You could either do v times u or u times v. It doesn't matter. You get the same result. However, I'm warning you now that in linear algebra, this is not a general rule. This is not true usually. The order that you write your vectors, and in the future matrices, is critically important. Because when you're doing some of these problems, the order will matter. The answer you get if you do it one way versus the other will be completely different. So just be careful about that. But for now, at least with the dot product, this is perfectly fine. You can do it either direction, you get the same result. But get into the habit right now of keeping the order the same every time. So if you're given a problem and it says v dot u, keep v on the left and u on the right. Whether it matters or not, it's a good habit to be in because later on it will matter very, very much. In fact, if these elements in your vectors are not scalars, let's say we're doing something like quantum mechanics, where the elements of your abstract vector in quantum space are actually operators, things like derivatives and stuff like that, then the order will matter. You won't get the same answer doing it one way versus the other. Because in one direction, you're taking the derivative of the second vector, and in the other direction, you're taking the second vector and you're multiplying it by some derivative of some unknown thing that's not even there. So they mean different things, generally speaking. If these vectors are just numbers, then the order doesn't matter here. Okay, now, another thing with dot products, what makes them very useful is what's called getting the length of a vector. Right? So let's say I tell you to get from my house to this store, I have to follow this path, this vector v. Right? And again, it's A, B, C. So I move A meters in the eastern direction and B meters in the northern direction and then C meters up and down. Maybe it's in a building or something. So second floor, third floor, whatever. But then someone says, okay, well, how far away is that? If I just wanted to go in a straight line from your house straight to that place instead of following this path, how far away is it? Well, we know in general physics when we did vectors, given a vector v, the magnitude of the vector v, which is the length, is equal to the square root of the x component squared plus the y component squared plus the z component squared. Right? Well, that's still true here. In fact, the length, we could call it v. This is actually not, well, yeah, we'll do it like this for now. Let's talk about the length squared first. The length squared means take the vector v and dot product with itself. Okay? That's the length squared. And of course, if you take the square root of this thing, you get the length. But it's easier to just initially do the length squared. So the dot product of a vector with itself is called the length, or the square, the length squared of the vector. So it would be ABC dotted with ABC, which is a squared plus b squared plus c squared. And of course, if we want just the length v, that's the square root of the squared length, or also called the magnitude squared, which would be the square root of a squared plus b squared plus c squared. And of course, this is the same as this, right? The x component of our vector v is called a and b and c for y and z directions. So that's another way of using the dot product that it's used actually quite often, finding the length of a vector. There's a lot more stuff we can do. Of course, we could do things like, how about take alpha times v and add it to beta times u. Right? So now we're combining different things. We're going to be adding two vectors, but those two vectors are also multiplied by scalars. Well, if we write it down, it's alpha times ABC plus beta times DEF. So that's alpha A, alpha B, alpha C, plus beta D, beta E, beta F, which of course becomes the vector alpha A plus beta D. That's the x component of our new vector. And alpha B plus beta E, that's the y component. And alpha C, beta F, that's the z component. So again, very nice, nothing complicated here. You have combinations of different operations. You just do the operations on each vector and then complete it however you need to complete it. Here, scalar multiply the vectors first, then add those two results together to get the sum of these two vectors. Anyway, for now, we'll end it here. That's the basics of vectors. We're, of course, going to get more into it. We're going to look at things like the cross product, which is the other form of multiplication we need to know about. And, of course, the big one, which is matrices. How do we deal with things a little bit more complicated, or at least, let's say we want to make things look simpler on the page. Instead of having 3 different vectors, and we're going to do some kind of a set of operations with all 3 of these vectors acting on some other vector, it can look a little messy. Or we can combine all of that stuff together into one object called a matrix, and now our equations will look a lot nicer. And there are plenty of rules that go along with how to deal with matrices, how do you use matrices with vectors, all sorts of stuff. That's where we're going in the future. But for now, I just wanted to relate those things we know from general physics, the basic vector manipulation, to this new form of vectors, this new kind of symbology, which is column vectors. And of course, we'll deal with something called row vectors later. And just get used to the notation. Because once we're used to the notation, all the rules are kind of already in the back of our minds. It's just a matter of getting used to using them in this new form. Anyway, hope this makes sense, and I'll see you later.